Hello everyone. In this class, we'll see one more topic on simultaneous material and energy balance. This time, let us include a process with the chemical reaction. So in my previous case where I used a drying operation, there was no reaction involved. It was a without reaction case. Now, we'll see a material balance and energy balance where we are going to consider chemical reaction also. Using a numerical, let's learn how to do it. Let's go ahead. Here is the numerical. You may pause the video. Yes, the numerical is lengthy. Please read it once. Once you have read it, let me explain you the concept, what is behind it. We have Saccharomyces cerevisiae yeast. It's grown anaerobically in a continuous culture at 30 degrees Celsius. That's fine. Glucose is used as the carbon source, ammonia is used as the nitrogen. Okay. A mixture of glycerol and ethanol is produced with a yield of 0.22 gram glycerol per gram glucose, 0.33 gram ethanol per gram glucose. Alright, so it means glucose and ammonia are the reactants, glycerol and ethanol in the product side. The yield is given to us per gram glucose. At steady state, the process is steady state condition. Mass flow rates from the reactor, so it's a continuous reactor. So mass flow rate is mentioned, so it means it's a continuous reactor, right? It's also mentioned earlier in the first sentence. And combustion data are given in the table below. The standard heat of combustion data is given. So for all the component, you have whether it is with coming in or going out, it's mentioned. Its molecular weight is mentioned. Mass flow rate is mentioned. So there are two things which is not known to us. Mass flow rate is not given. However, its yield values are given, right? 0.22 and 0.33. 0.22 for glycerol, 0.33 for ethanol. Biomass molecular weight is not given. Okay. Then standard heat of combustion data is given for glucose, ammonia, glycerol, ethanol and biomass. Note that biomass unit is different for standard heat of combustion compared to the other things. Carbon dioxide and water are the products of combustion, so obviously they do not have standard heat of combustion, that will be 0. Okay, CO2 and H2O, the standard heat of combustion is 0 because they are already the products of combustion. The question is estimate the cooling requirement. How much cooling load is required? Okay, the heat is being generated because of heat of combustion, that is the heat of reaction, right? Because of the heat of reaction involved here, exothermic reaction, heat is being released, and that heat needs to be taken out, otherwise the cells will die. So heating requirement is required, and you need to remove it. So let's do a material balance and energy balance for this case. Let me take the basis as 36 kg per hour of glucose fed to the fermenter. Let me not convert this per hour concept, that is let it be in hour operation. Steady state process with the energy okay, no energy loss or no mass loss, we'll consider it. This is the fermenter. What we are doing, we are feeding the feed glucose and ammonia, carbon dioxide is going out, cells, biomass, glycerol, ethanol and water are parts of the product. So these are the products, and the heat is being released out, taken out by the cooling liquid. This is very important, right? So if you have the masses and the heat coming into the picture of a block diagram. Let's look at the data that is available to us. Let me give some notations to it. Y is the yield, glycerol upon glucose, ethanol upon glucose, 0.22 and 0.33 gram, glycerol per glucose and ethanol per glucose. So this data given in the numerical, so I am rewriting it. Then the table what is given, I rewritten this, okay, I rewritten the same content as it is, not changed anything till here. The standard heat of combustion, since the data is available in kg per hour here, mass flow rate is in kg per hour, and here it is in moles, and here it is in gram, let me convert that information to per kg. How do we do it? If you have a data in kilojoule per kg, I mean required in kilojoule per kg, the data that is available in kilojoule per mole, you have to divide it by molecular weight. That gives you the kilojoule per gram, but we need it in kg, right? So multiply by 1000. So in simple, the value you look here, multiply by 1000 divided by molecular weight, right? So that will be in kilojoule per kg for these four values. All right, this is 0, whereas here it is already in gram. You just have to multiply it by 1000, so it becomes kilojoule per kg. So this is different from these conversions. Let's write the stoichiometry based on the available information here in and out. glucose in, ammonia in, biomass out. It's not balanced reaction. We need not write the balanced reaction because biomass molecular formula is not known to us, not even molecular weight. So we may not be able to write the balanced reaction. It's an unbalanced reaction. But however, based on the mass flow rate, you can do the balancing. Alright, this information is available to us. This leads to a mass balancing. Output is biomass, glycerol, ethanol, carbon dioxide, water. Based on this information, it's written. Now let's take a steady state mass balance over the fermenter. What comes in, that goes out because it's a steady state. So the glucose and ammonia mass comes in, biomass, glycerol, ethanol, carbon dioxide, water. This mass goes out. They are all products, right? Now balancing it, out of this, the glucose and ammonia known to us, biomass is given to us. It is given in the table here. Same values, mass rate it is given here. These values are written. Glycerol and ethanol mass flow rate we do not know, not given there, question mark. Whereas carbon dioxide, water it is given. So if you simplify this, these two things, glycerol and ethanol together, mass flow rate is 19.84 kg per hour. But still, we may not be able to solve this because there are two components, together it is 19.84. We require one more information. It's already available in the form of data, yield data there. So using yield, the meaning of yield is per gram of glucose this much glycerol is produced, but the glucose fed is 36 kg per hour, right? So for 36 kg per hour, how much it is being produced? So you can calculate, that is 7.92 kg per hour for glycerol. Ethanol it is 11.88 kilojoule per kg per hour. If you add the two things, right, roughly it will be 19.84. Maybe because of decimals of accuracy you get the difference, slight difference. These two when you add it, it will be 19.84 kg per hour. So our mass balance is solved. Now let's go ahead with the energy balance over this fermenter. So enthalpy of flowing in with the streams. Look at the material balance what we have in the block diagram. Okay, so you have the components coming in, getting mixed with the reactor, heat is left out, then it goes out, right? Continuous reactor. So there must be some enthalpy that is coming in with the reactant, and that will be equal to enthalpy flowing out with the product, that is energy going out with the product because of the flow. These two are because of the flow, plus heat given out to the cooling fluid because it's an exothermic reaction. It delivers the heat and taken out by the cooling fluid. So it is an exit, heat is exit. Then minus, you have the heat heat of reaction, that is exothermic reaction, right? Heat of reaction, yeah, I think heat received by the cooling fluid will be equal to heat of reaction. These two things, the main intention behind this one is these two things, that is enthalpy of flowing out with the product. This is a different line, please read this as a different line. This line is a different from this. Equation stops here with the three terms. So enthalpy of the product minus enthalpy of the reactant, we call it as heat of reaction. Since it goes on the other side, it will be minus. I have written, for that reason I have written minus here. Okay, so heat of reaction is minus in this, I mean notation is minus here because this product, it goes on the other side. Reactant minus product you will have to write will be equal to heat given to the cooling fluid or heat received by the cooling fluid, right? So that will be equal to minus of heat of reaction. In notation point of view, it is minus delta HR is equal to Q. That is the cooling requirement. Now this is the question mark. Q you have to find out. If you find out delta HR, that will be the requirement, heat of reaction. How do you find out the heat of reaction? Based on the heat of combustion data or enthalpy of reaction, you can calculate. We have the standard heat of combustion data for per kg, kilojoule per kg we have, but it's not kg here, it is kg per hour of each component we have. So let us do it for the glucose, let us do it for the ammonia minus biomass minus glycerol minus ethanol. Alright, so standard heat of combustion data, always it is delta H of the reactant, delta H combustion of the reactant minus delta H of the product for the combustion data. The reason is the combustion data is already negative, for that reason it is always reactant minus product, whereas any other case it will be product minus reactant. For the combustion case, when you have a combustion data, always it is reactant minus product, the standard heat of combustion value when you use it. So the M is the mass flow rate of each component, substitute, Here it is 36 kg, 0.4 kg, 2.21 kg, 7.94, 11.9, like that. Then you have the standard heat of combustion. This is the data what we have already calculated in the table. Substitute, and roughly you will get minus 13,920 kilojoule per hour. It's per hour mass here, right? Kg per hour, whereas delta H is kilojoule per kg. So the unit will be kilojoule per hour. And this is the negative value when you do the substitution. So it's minus of minus. When you substitute here, Q will be a positive value, right? Q is a positive value, minus of minus. That means you have to uh, remove the 13,920 kilojoule per hour at that particular rate. You have to remove the heat, right? So in this problem, what did we observe? We have seen the material balance. We have a fermenter in which exothermic reaction is going on. You will have to do the material balance first, so that you get to know what is the quantity of all components produced, and based on their heat of combustion data, you have calculated heat of reaction, and that will be equal to cooling requirement, and based on that you have calculated the cooling requirement. So here I have one more problem for you. I expect you to learn on yourself. You have been given with the notes material for this, right? So it goes with the same similar strategy. In addition to it, you have aeration coming into picture, oxygen coming into picture. Here it's an aerated reactor, and you have agitation, power input. So mechanical agitation delivers heat to the system, so that's a plus to the system. Also there is a evaporation loss. 100 kg of water is lost from the medium. Because of that, energy is also lost along with that. So this is minus to the system. So these two things if you include, then cooling requirement you have to calculate, right? And that is in terms of energy analysis. Yeah, you can go through the notes for the solution of this with this particular concept. Otherwise it remains almost similar to this. That's it for this class. Thank you.